Moment of inertia. Torque is the rotational analog to force, Rf sine theta. Newton's second law states that F equals ma, force equals mass times acceleration, and this has been applied to point particles that don't rotate, or the center of mass of an object that doesn't rotate. For example, we have a box, we push the box has a certain mass, therefore it will accelerate with a certain acceleration. We now want to analyze extended rigid bodies that do rotate. For example, a wheel, or a solid cylinder, or a marble. What we're going to do is we're going to start by analyzing the force on just one small piece of this object as it's rotating. So if this is our axis of rotation, let's say this is a wheel, and it's going to rotate this way. What we're going to do is we're going to pick one tiny piece of it, and we're going to call that I. So the force exerted on I is going to be the mass of I times the acceleration of I. And since it's rotating, and we can use this conversion here, the linear acceleration of piece I is going to be r alpha, right? It's going to be the distance from the axis of rotation times alpha, the rotational acceleration, right? All of the pieces on this wheel, they all have the same alpha. They don't all have the same linear acceleration, but they do have the same rotational acceleration. Let's continue on the next slide. All right, I'm going to draw my wheel again. Here's my axis of rotation. Here's our little piece I that we're analyzing. I'm going to write that a little neater. That is I. Okay, let's assume the force on little piece I is perpendicular to the line that connects piece I to the axis of rotation. Therefore, sine theta is going to be 1. We don't have to worry about it. Therefore, the torque on this little piece I is r times F, because we got rid of the sine theta. So r sub I is the distance between the axis of rotation and I. F sub I is the force on piece I. Now on the previous slide, using F equals ma and replacing A with r alpha, we have the force on piece I. It's the mass of I times the distance to I times the rotational acceleration of piece I, along with every other piece, right? They all have the same, every piece of this wheel has the same rotational acceleration. So we have two RIs, so it becomes the torque on piece I is mi RI squared times alpha. If we then sum up the torque on every little piece of the whole wheel, everywhere that there's mass, right, then we can do a summation. Now, we had alpha in here, but we can actually take the alpha out. We can factor it out. Why can we do that? Well, because alpha is the same for every little piece. So because it's a constant, we can just take it out and multiply it to the sum at the very end. This looks very similar to Newton's second law in translational motion. So remember, it's net force equals ma. This looks very similar. Net force has been replaced by net torque, and A has been replaced by alpha. All good. However, M has been replaced by this, the summation of mi RI squared. This is a new concept called the moment of inertia, I, capital I. The mass of a given rigid object is always constant. Can the same be said for the moment of inertia? So for example, if this was a wheel, the mass of the entire wheel, m, that's just a number. However, the moment of inertia of an object, is that always constant? No. It depends on the configuration of the rigid object and where its axis of rotation is located. Here is Newton's second law for rotational motion. Net torque equals I alpha, where I is the summation of mr squared for every little piece of mass in that object. If more of the little pieces of the rotating object are located further away from the axis of rotation, then its moment of inertia will be greater than an object of the same mass where more of the mass is concentrated near the axis of rotation. Let's see what this means. Here are various moments of inertia for common objects. All of the objects have the same mass, m, but they have different shapes and different axes of rotation. Take some time to see how and why the moments of inertia change. For example, if we have a solid sphere, like a marble, and we have a thin spherical shell, they have different moments of inertia. A solid sphere is 2/5 mr squared, whereas a thin spherical shell is 2/3 mr squared. 2/3 is a larger number than 2/5. Why is that? It's because more of the mass is farther away, right? It's at a radius, a distance of r, whereas in a solid sphere, some of the mass of this object is located very close to the axis of rotation, which when we have mr squared, if r is 0 or close to 0, that mass doesn't contribute to the moment of inertia at all. If you rotate a stick in its midpoint, more of its mass is very close to the axis of rotation. So you're going to have a lower moment of inertia than if you rotate the stick at its end point, so now you have mass that's very far away, and right, r is squared, so that distance means that that piece of mass will contribute greatly to the moment of inertia. Mass is a measure of an object's resistance to acceleration due to an applied force. Moment of inertia is a measure of an object's resistance to angular acceleration due to an applied torque. The greater the moment of inertia of an object, the less it will accelerate rotationally due to an applied torque. The same torque is applied to a solid cylinder and a solid sphere, each with the same mass and radius. Which object will have a greater angular acceleration? Since the solid sphere has a smaller moment of inertia, it will have a greater angular acceleration. The angular acceleration can be different for the same object if a different axis of rotation is chosen. Which would be easier, getting a ladder to rotate by holding it in the middle or by holding it at one end? It should be held in the middle. By rotating it about that axis of rotation, the rod has a smaller moment of inertia, so for a given torque, it will have a greater angular acceleration. It will be easier to rotate. So here we see the moment of inertia of a thin rod being spun through its center is 1/12 ml squared. And over here, if you hold it by one end, it's 1/3 ml squared. 1/12 is less than 1/3. Therefore, the rod on the left, rotating through the center, has a lower moment of inertia and is therefore easier to rotate. Remember, for a constant torque, if we rearrange Newton's second law, net torque equals I alpha, if you solve it for alpha, so divide both sides by moment of inertia, we get rotational acceleration equals net torque over I, moment of inertia. So therefore, angular acceleration and moment of inertia are inversely proportional. The larger the moment of inertia, the smaller the angular acceleration, and vice versa. If the moment of inertia about the center of mass of a rigid body is known, the moment of inertia about any other axis of rotation of the body can be calculated by use of the parallel axis theorem. This theorem will be presented without proof. The new moment of inertia will be the moment of inertia about the center of mass plus md squared, where d is the distance between the new axis of rotation from the original axis of rotation through the center of mass, and m is the total mass of the object. Let's apply this theorem to a solid cylinder of mass m and radius r. The moment of inertia when the cylinder is rotated about its center, so if it's just spinning, is 1/2 mr squared. Find the moment of inertia when it's rotated on an axis parallel to its central axis and at a distance r. So now we're going to be rotating this cylinder about its side. So it goes all the way around. It's not just spinning in place. We start with the parallel axis theorem. We put the original moment of inertia through the center of mass here, and we add md squared. But instead of d, we put the distance that the axis is moving. So it's going from here to here, which is a distance of capital R. So we replace that d with capital R, and then we simplify. What torque needs to be applied to an antique sewing machine spinning wheel of radius 0.25 meters and mass 4.2 kilograms? Model the wheel as a hoop with its moment of inertia equal to mr squared to give it an angular acceleration of 5.6 radians per second squared. All right, so we're going to start with Newton's second law, but instead of F equals ma, we have torque equals I alpha. Because the moment of inertia is mr squared, we're going to go ahead and plug that in here for our moment of inertia, and then we're going to plug in our givens, and we get 1.5 Newton meters of torque. All right, two masses, one with mass m, the other with mass 2m, are attached to a light rigid rod as shown. What is the net moment of inertia of the system? This is the type of problem they could ask you on the AP test. They could ask you to calculate the moment of inertia for a very simple configuration of masses that are attached by something that doesn't have mass. So you don't have to consider the mass of the rod itself. So we're going to treat each mass as just a point mass, and we're going to use the summation of mr squared for each mass to calculate the moment of inertia by hand. So for example, if our pivot is here, this is a length L, this is a length 4L, we can use the sum of the moments of inertia is going to be the total moment of inertia. So for mass 1, we have the 2m. So we have 2m and then r squared. R in this case is L. So we get 2ml squared, right? We're just using mr squared for each of the masses. Then for this mass, we have a mass of m here, but it's a distance 4L. And that 4L gets squared since it's mr squared. So then, therefore, we get a moment of inertia of 16ml squared. When we add those together, we get the total moment of inertia of this object, 18ml squared. A rod of length L is rotated about its center, which has a moment of inertia of 1/12 ml squared. What is the moment of inertia at a point L over 4 away from the center? So we want to know there. So this is going to be L over 4. This is then also L over 4. From here to here is L over 4. Here to here is L over 4. So those all add up to L. So we want to know if we change our axis of rotation from being in the center to being here, what's our new moment of inertia? For this kind of problem, we can use the parallel axis theorem. So we already know the moment of inertia through the center of mass, 1/12 ml squared. So all we have to do is add md squared, where d is the distance between where the axis of rotation currently is and where we are moving it to. So that distance is L over 4. So we have m times L over 4 squared. And once you simplify this, find a common denominator, etc., you get 7 over 48 ml squared. A massless rod is connected to two spheres, each of mass m. Assume the spheres act as point particles. What is the moment of inertia of this configuration if the axis of rotation is located at one of the masses, for example, here? What is the moment of inertia if the axis of rotation is located at the midpoint of the rod? Which is easier to rotate, and why? Alright, so if we make our axis at one of the spheres, then we have one mass at a distance of 0 from the axis of rotation. So this mass doesn't contribute at all towards the moment of inertia. We have the other mass at a distance of L, right? If we assume the length of the entire rod is L. That's how far away it is. So therefore, the total moment of inertia is ml squared. Here, however, in the middle, we have one mass at L over 2. We have another mass at L over 2. When you simplify this, you get 1/2 ml squared, which is half of the moment of inertia as when you had it at the end point. The rotation about the midpoint is easier since the moment of inertia is smaller and provides a smaller resistance to rotation. A group of students do an experiment where they hang a mass from a pulley and then measure the angular acceleration of the pulley. Given the data set, what is the moment of inertia of the pulley? Hint, draw a graph. Alright, so we're going to draw a graph, and we're going to put alpha on the y-axis because it is the dependent variable. The angular acceleration depends on the applied torque, and it's inversely proportional to the moment of inertia. So if we graph this data here with alpha on the y-axis and torque on the x-axis, what does that make the slope of this line? So to help us out a little bit, let's separate these two variables. Instead of just net torque over I, we'll make it 1 over I times net torque. And now it's clear to see that if this is y and that is x, that means slope is 1 over I. The inverse of the slope of this line is the moment of inertia. Since the slope of the line is 3, you can calculate that using rise over run, the moment of inertia is 1/3 kilogram meter squared.